Okay.
Welcome to Science for the Board. And we have a modest audience so far tonight, but this is going to be real physics. So fasten your seatbelt. Ed Friedman is going to be talking to us. Ed?
Yeah, thanks. Maybe some of you didn't hear what I'm about to say. I'm going to show something a little different tonight. You should be seeing the Microsoft Word page. I can make it a little more streamlined. This presentation is based on a book I've been working on for about 3 months on the topic of cosmology. It's divided into 2 sections. The first part of it is concepts. It focuses on the big ideas in cosmology. And there's about 14 chapters of the conceptual material, semi-technical, no equations, but graphs and other things. And then there are appendices, I call them annexes, where I have actual math, and I'll show you a little bit of that tonight too. So, and I encourage you to write to me if you want to get access to the draft material that exists, and take a look at it, see if you have feedback for me. So let's get into this. I'm going to concentrate on one of the chapters called Expansion of the Universe. This has a great history behind it, and what's more, it includes a lot of conceptual challenges that I try to lay out very clearly for those who haven't had the time to go through it like I have. The concepts involved are perplexing because we live in an expanding universe. So you see text here referring to Edwin Hubble. He was not the first, but he was the most prolific in discovering the relationship between the distance to astronomical objects, principally galaxies, and the velocity at which they are receding. And he turned this into science. And he had modest, at the time, he was in the 1920s, he had modest telescopes to work with. But he really started, along with Einstein and a few others I'll introduce, he really started our understanding that's depicted here of an expansion from a big bang, here designated as quantum fluctuations. We really don't know what happened. And then an explosive size increase that's associated with the word inflation. I'll talk a little bit about that tonight. And eventually we get to a point where the hot plasma of the atmosphere of the universe cooled enough that atoms could form and be stable and light could propagate. And that's what this ellipse here indicates. These green and blue colors indicate that's the cosmic microwave background that I've talked about before. And we see it today because the universe has been transparent since this era, 375,000 years after the big event. But there were no stars when this what is now seen as microwaves, there were no stars. So we have this interval of darkness for about 400 million years before clouds of nitrogen got together and formed the first stars, and right after that, the first galaxies. But there was total darkness in the universe. And then we began to have a proliferation of stars and galaxies. And this drawing is supposed to indicate that we had this rapid inflation, and then we had kind of a slow growth indicated here, but that right here, we've had this uptick in the rate of expansion that is now affiliated with what is called dark energy. And I'll talk about each of the phases depicted in this piece of art. Now, Hubble was very influential because he saw evidence of expansion, but at the same time, Einstein had just finished developing his theory of gravity, roughly 1917, and he had a small cadre of collaborators including Alexander Friedman and Lemaitre, a priest who was very adept at dealing with Einstein's theory. And they were, Friedman and Lemaitre actually were able to use his theory and guess about certain properties of the universe and predict future patterns of growth or collapse. And I'll show you that here in a second. So a lot of research is started in the 1920s. And of course, the great telescopes we have now are adding information all the time. And indeed, we now know from measurements of different kinds, independent measurements, that the matter we are made of makes up about 5% of the energy in the universe, actually a little less. So this is atomic matter, and that includes all the stars, the galaxies, the gas, everything made of atoms accumulates to just under 5% of the energy in the universe. Dark matter, which is mysterious, nobody knows what it is, everybody's scrambling to figure that out, that accounts for 25% of the energy in the universe. So all the matter together is 30%. And the rest of the energy in the universe is all what is now called dark energy, also a mystery. We'll talk about a bit about that tonight. So if you want to look at this in a pie chart form, today we have this distribution of forms of energy in the universe, and dark energy really dominates the stage about the increase or expansion of the universe because it propels an accelerating expansion. So here's the atomic material, just under 5%, and dark matter, 23%. The early universe was quite different. That's shown here, where dark matter was dominant. Dark energy, which is associated with some kind of strange behavior of a vacuum. So that is, if a vacuum is created in the universe, dark energy immediately jumps in there and adds more energy by a mechanism that we do not understand. But in the early small universe, there was essentially no dark energy because the universe was dramatically smaller than it is now, more than 1,000 times smaller than it is now. So dark matter was important and dictated the formation of galaxies. Neutrinos and photons, or light, they have faded from the scene. They are insignificant now because they've been diluted by the enormous expansion that's occurred over the last 13 to 14 billion years. In most of this talk, I'll say 13.8. Some of this artwork has 13.7 for the time since the Big Bang. So here's a little detail about what Hubble did. And this is in fact a graph that he drew back in the late 1920s, where he was measuring the distance to galaxies and measuring their velocity using redshift, that is looking at the shift in spectra of the galaxy and comparing it to the same spectrum, let's say of hydrogen, done in the laboratory. And by using that shift, he could deduce the velocity. And so he got data like this using relatively small ground-based telescopes at Palomar and so forth. Now, we've done a lot of work since, and this graph that I'm showing here, this is Hubble's work, appears on this chart as a red line. That is, here's distance. And he was restricted to right here, about 30 or 40 million parsecs. A parsec's about 3 light years. So his reach out into the galaxy or out into the universe was limited. And he got these values for velocity. We now know his numbers were dramatically wrong. And that was important because all scientists, including geologists, were watching what Hubble was doing. And he came up with these expansion rates that were so big that and there's a relation between the expansion rate and the age of the universe. The bigger the expansion rate that you deduce, the younger the universe is. And geologists were regularly pointing out that Hubble's work predicted that the universe was so young that rocks known to exist on Earth that were 4 to 5 billion years old were older than the universe in his conjuring of the data. So now it's modern times, and we have Hubble from the Hubble Space Telescope looking at supernova events. That's now the standard method for measuring distance and velocity, and we get a very, very different result. And the slope of this curve that we have here is close to what we now call the Hubble Constant, and honors the contribution of Hubble, even though his initial data were a little out of kilter. So at this point, I just want to point out that all the artwork in the book is surrounded by this narrative to help make it digestible to non-scientists or non-specialists. So here's the kind of thing that, there are actually two pieces of art here that Friedman and Lemaitre came up with. If there was enough matter in the universe, and if you put that large fraction of the universe being matter as opposed to light or dark energy, if you put that in Einstein's equations, you get a universe that grows and then collapses. So time goes upward on this graph. There's a kind of a balancing act. If things are just right, you have a growing universe that started small and grew. They have another version of this called a coasting universe. Once again, the distinction between these is based on what fraction of the energy in the universe is dark energy versus matter. Based on what we know today, this is the right answer. Because as the universe expands, the vacuum created gets filled with dark energy, and that propels more expansion. And it's a runaway system. And this was not known 25 years ago. It was first detected in the very late 1990s using the repaired Hubble Space Telescope to measure the distance to supernova events, and led to a Nobel Prize for Adam Rees and his colleagues. The accelerating universe is a very, very recent idea. And you can see it here. These are depictions, just a slightly different way to show what Friedman and Lemaitre predicted. This orange one is a heavily dominated by matter. It's a universe that grows and collapses. All of these are set to be the same size now. So a universe filled with matter just grows and collapses under the weight of gravity. And the universe we see is this one that I showed you these numbers before, and I'll keep repeating that the amount of matter in the universe is 30%. And the dark energy is 70% of the energy in the universe. And that leads to this runaway curve here. So the universe is, the way we see it now, the universe is going to continue to grow in size, and its rate of growth will continue to increase. Now, I've redrawn that prior curve this way because there are some simple algebraic forms you can see here. For the universe that's dominated with matter, the universe grows like the square root of time, the size and the time are related by a square root. If you have a balance, nearly a balance between matter and energy, then it grows at t, the size depends on the time to the 2/3 power. But if you have a universe dominated by dark energy, it's an exponential growth, and I shifted it so they all start at the same point. And this is what we think we're going to see. So a typical question at this point is, well, what is the universe growing into? And the answer is it's not growing into anything. The best hope we have for understanding this is that a pair of ants who are confined to the surface of a sphere and they have no concept of up and down. They can go forward, backward, left, and right. But they're confined in their geometry to the surface of a sphere. And if the sphere gets bigger, they notice they get farther apart. If they send signals to one another, it takes longer for the signals to convey from one place to the other. So this is this is the best we can do in terms of visualizing what is going on in our universe. And at this point, I'm just going to make a statement and I'll back it up later. And that is, there's a difference between geometry and shape. And I'll show you examples of that. And I hope that that concept allows all of us to embrace what's going on in our universe. Our universe has no edge. I want to emphasize that too. These ants can go on excursions all over the place. They never encounter an edge. In fact, if they travel fast enough, or their universe is growing slow enough, they can go in any direction they want and they'll come back to where they started. And there's a lot of evidence that that's the way our universe is constructed, with a proviso that I'm not going to reveal just yet. So ants on a sphere is the way professionals deal with this. If you read Brian Greene's books, he has a grasp of all this, but he makes the point that when the professionals are at the blackboard sketching out what's going on with the expanding universe, when they start visualizing this, they always go to ants on a sphere or balloon. And if they're going to get quantitative about this expansion, then they start doing math, because nobody can visualize how this works, because you have to have an extra dimension to see these ants confined in their world. But we'll get into that in a minute. Just a historical note, this is the Hooker telescope that Hubble used. This was the bigger of the telescopes he had access to. He might be in this picture. I thought he was, but apparently not. Okay. So now let's talk a little bit about the conceptual challenge of what it means for an object. Principally, we're dealing with galaxies. What does it mean for a galaxy to be in an expanding universe? And the way to deal with this, I found, is to consider a river and a boat and an observer on the shore. If a boat goes by and you observe this boat going by, it could be moving for two reasons, at least two reasons. One, the river is flowing and carrying the boat along. But the boat, in that case, the boat is static in the water in which it's sitting. The other possibility, a second possibility, is the boat is being propelled by these oars. So it's moving through the space in which it's floating. And the third possibility is both of those things are happening, that the river is flowing and the boat is moving. And this applies directly to what we see when we look at galaxies like Hubble did. Hubble did not understand this. At the time, the standard concept for the cosmos was the universe was static. And that had been the dogma for decades prior to his work in the 1920s. So he knew he was detecting redshift or Doppler shift. He called it Doppler shift, galaxies moving away from him. And he presumed that the space in which they were moving was static and the galaxies were moving in their local space, just like if this water was static and the boat was being rowed. We now know that's not the case. The case is that the motion of the galaxies in their environment is very small compared to the expansion of the space between galaxies. The most distant galaxies are going away from each other faster than the speed of light. I'll show you that later. And they do have motion in their environment, but it is trivial in velocity compared to the influence of the expanding universe. And I have this drawing here to illustrate why an expanding universe makes the most distant objects recede faster. So we have, imagine this is a slinky. And you're holding on to this end called A and the other end is B. And then somebody pulls on B. And if they pull enough for A to the coil to move from here to here, the B coil doesn't just move by one unit here. it moves by several units, moves from here to here. And if A moves 2 units from here to here, this one moves way out to there. So we see exactly what Hubble saw, the most distant objects moving fastest and closer objects moving slower. Now, in all cases, Hubble had, and modern astronomers have to ignore the very closest objects, like Andromeda Galaxy is close to us. And it's actually moving toward us because it's under the influence of the gravitational pull between Andromeda and our Milky Way galaxy. So I hope we've overcome some misconceptions by talking about the fact that the way we interpret the universe now, galaxies are being carried away from us because the space between them is expanding. Not almost ignorably are the galaxies moving in their own space. So let's talk a little bit about how the expansion rate has changed over time. So it's traditional to use this parameter A, shown here. A is the relative size of the universe compared to now. So if we look at this curve and we go to...
And I'm sorry, can I just ask a question here?
Of course.
Yeah, this is Dan. I'm just going to ask, so you say the space is expanding, but to me, space is simply the distance between 2 objects. So I understand you're saying that the water is moving, making the space between you and watching the boat changing. But you're saying now that the space is changing. So the water is moving, but to me, space is simply the measurement of the distance between 2 objects.
Yeah. And
so space is expanding. How, especially in the case of the universe, space, which is really nothing, how could it expand?
Okay, so let's go back to our...
I'm sorry, I don't want to send this back to square one, but...
No, it's
okay.
We covered this. So the river analogy does fail. And actually, what I'm going to do, because I like something you said, I'm going to write myself a little note. I'm going to expand this explanation.
Okay. I mean, I like it. I like the idea of the river moving and the boat moving. But to me, space is still just the distance between what you see and what is there.
Right. So let's go back to our ants on the sphere. If
Okay.
this is a balloon and I can inject some air into the balloon, the actual space between these ants will grow bigger.
Yes.
And that's what we observe in the universe. If we look at galaxies, in fact, parameter A, which I was just about to talk about, parameter A is a measure of how the distance between galaxies changes over time. And we can detect how it's changed over time because telescopes are time machines. We can look at a galaxy, and by looking at its redshift, we can tell how old it is, how long it's been since its light came to us. And what I've depicted here is that right now, the reference, the value of A for today, which is right here at 13.8 billion years, we call that 1. So in the past, the universe was literally smaller. All the galaxies were closer together. The galaxies themselves were not smaller because gravity dictates how galaxies and planets and atoms and people how their size changes. This expansion we're talking about is the invention by the universe of new space between galaxies. And that is measurable, and we have data to confirm this part. This is what we induce or deduce from seeing the old expansion and using Einstein's equations. And we see this as the future for the size, how the size of the universe is going to change. So we can say we're at this reference size 1 right now. If we want to find when is the universe going to be twice as big as it is now, we go over here and come down around 23 billion years after the Big Bang. it will be twice the size it is now. And that growth rate is not a straight line. It has an upward slope to it. So I thank you for the question, because I'm going to fix
So,
something.
so just to go back, so the galaxies won't be all that much bigger, but the space between the galaxies will be that much greater. It'll be double.
Right. In fact, the galaxies don't
All
change
right.
size at all. In the book, I have a reference to a video clip from a Woody Allen movie. I'll describe it to you. Woody appears in the movie as a 12-year-old, and his mother takes him to the doctor. And she's frantic because he won't do his homework. And the doctor, who is busy smoking one cigarette after another, says, "What's the problem, young man?" He says, "The universe is expanding. So why should I even bother doing my homework? Because the whole universe is going to blow up." And the doctor says correctly, the Brooklyn, where we live, is not expanding.
Right.
The universe is
Okay.
expanding, but Brooklyn
Thank
is
you.
not expanding. And the doctor is absolutely right. And then he takes another puff on the cigarette. So, now,
I like that. Thank you.
okay, so now here's a little more history on the expansion rate. I want to emphasize that the universe has, as far as we know, never gone through a period when it was not expanding, but its rate of expansion has changed since the Big Bang. In the early universe, its expansion rate, those who've had calculus will recognize this is the time derivative of parameter A. The expansion rate in the very early universe was enormous compared to what it is today. And because matter dominated, the universe, when it was small, contained very little dark energy. And dark energy is the propulsion mechanism for the expansion. So the universe started out under the influence of the Big Bang with an enormous expansion rate, but it was slowing down. The expansion rate was slowing and had a minimum right about here at about 7.5 billion years after the Big Bang event. The universe now was big enough that dark energy was prominent enough that it took over and began to dominate. And from that point forward, we have an accelerating expansion. So we've seen, once again, we live right here. So when we look back at galaxies, the most distant galaxies are the oldest ones, and we can see the expansion rate they had. And we put that into Einstein's equations starting here, and we can see this expansion. Now, the Hubble constant, which is, if you follow the astronomical news, you know there's controversy about the Hubble constant, H. It is the ratio of this curve to this curve. That is, the rate of expansion divided by the size of the universe at any given time gives us the Hubble constant. And from this, we derive that the Hubble constant was very large in the early universe. We are right here, right now, just about right there, at 13.8 billion years. So the Hubble constant has been drifting downward, and because of the influence of dark energy, eventually the universe is going to be so big that the influence of matter in the universe will be diluted, and everything will be dictated by dark energy, and the Hubble constant will become literally a constant. The reason it's called a Hubble constant is the presumption is it's the same everywhere in the universe at any given time. But over time, the Hubble constant has decreased and decreased, and it's eventually going to settle into a number about 10% smaller than it is right now, which is right around, it has these odd units. If you want to talk about those, write me an email, we can talk about them. But eventually the Hubble constant will be a time constant as well as a spatial constant. Now, here's just a little more on the issue of the redshift. This is literally how we get redshift. We look at the spectra, these dark lines are the spectra of, say, calcium seen in a galaxy. And we measure the absorption lines of calcium in the laboratory so we know what's going on at an atomic level. But then we look at the galaxy and we get these numbers. And that increase is due to the expansion of the universe. And it's because virtually everything in the universe appears to be going away from us, except for nearby objects like Andromeda. Because everything's going away, light is stretched during its flight to us, and it becomes redder. That is, it moves towards longer wavelengths. And so it's called redshift. If you go out and measure the spectra of Andromeda, you'll see it's blue shifted because Andromeda is in the grip of the gravity of the Milky Way. The two of them are attracted. And so the Andromeda in 3 or 4 billion years is going to merge with the Milky Way or pass through the Milky Way. And we can see this another way too. There are these supernova events. One of them is pictured here. This is actual data. We know from the chemistry of supernova events that the supernova explosion of a star peaks and then fades away. I'll show you why that happens in a minute. And we know how long that takes. It's a little hard to see, but it takes about 30 days for the explosion to fade away as the radioactive materials in the explosion decay away. But we don't see 30 days. We see more like 100 days of this kind of event, because the time it took the event to occur where it occurred gets stretched as the radiation propagates to us and we detect it. Now, here's a little history to put in the context of Hubble's measurements. Here are Hubble's measurements back in the 1920s and 30s. He got these very big numbers, much bigger than we have today. And then over time, the techniques have improved, and we've now settled in at this number 70, roughly 70. The party's not over there though, because we have multiple ways to measure the Hubble constant and they don't agree. And this is one of the biggest mysteries, along with dark energy. It's one of the biggest mysteries in cosmology today is, why can't we get the same number if we use this technique, this blue kind of triangle? That comes from looking at supernova events and Cepheid variable stars. The gray comes from looking at something called the cosmic microwave background. And this orange or red comes from something having to do with the aging of giant stars. And then they don't agree. This was a non-problem 15 years ago or 10 years ago. And in 2010, this is where we were. And the error bars for the different techniques overlapped sufficiently that nobody realized there was going to be a problem. Just 2 years later, people had improved their measurement methods. And then we began to see this gap. Like, this doesn't agree at all with this. It's a 10% error, and that's just bizarre. And the question is, why do we care so much about the Hubble constant? And it has to do with this. This is a depiction of what's called the cosmic ladder. It's very important. It's critically important that we know the distance to objects that we measure, that we see, such as exploding stars, so that we get the distance and the velocity from the same object. Measuring velocity is not hard, that we can use the same concept that Hubble used. Measuring distance is hard. So we have multiple rungs on this ladder. I mean, we can see the motion of Venus and planets using radar. Not a problem there. We can see the motion of nearby stars in our galaxy by using what's called parallax. You take a picture of the star, a star, this one, with its background, distant stars, in June, and then take the same picture in December, and this foreground star will have appeared to move. And you can work your way out to a few hundred light years in the galaxy and get the distances pretty accurately. But the Milky Way is 200,000 light years in diameter. And as things start getting fuzzy out there about getting the distance to the stars, we have now a very successful spacecraft mission called Gaia, built by the Europeans, that's doing a fantastic job of improving parallax measurements in the galaxy and is measuring the positions of millions of stars. But if we want to go outside the galaxy, which is where you have to go if you're going to talk about cosmology and expansion of the universe, you need another technique. And that has to do with exploiting variable stars, their brightness and the period of brightening and dimming are correlated. This was discovered in the 1920s, and they occasionally are near an exploding star. So over 50 years of research, people have calibrated how much energy is released when a particular type of white dwarf explosion occurs. And people are using white dwarf explosions, supernova events, as standard candles. Like you can imagine measuring the distance to a car, it's far away from you, but if it has a headlight on and you know the optical amount of optical energy being issued by the headlight, you measure that, what you detect, and you can discern the difference. You can discern the distance. So we have this complicated thing, and the Hubble constant is part of that calculation. So there's a little information here about the key technique for measuring distance right now, supernova type 1A events. This is what Adam Rees and his team used to win. He and the team at the Cal Berkeley won a Nobel Prize for this. Now, I mentioned that we understand what goes on in these supernova events, and here's why we do. Here's an example of actual data from a supernova event. The star explodes, it gets brighter, and if it behaves this way, we know what kind it is, where it dims like this and then starts drifting down. And the reason it does that is right here at its peak, it has produced an enormous amount of radioactive nickel. And we have measured the half-life of nickel. We know all about it. And so for a long time, for the first 20 or 30 days of the supernova event, the decaying radioactive nickel leads to this kind of light output from the star. But eventually the nickel arrives at multiple half-lives and becomes insignificant compared to the radioactive decay of cobalt. And this is the cobalt curve. So this is the typical thing we see. And here's a group from 22 different supernova events of type 1A, and you can see how they're all clustered together. And this is the peak we understand the energy released at the peak. And if you know the energy, you can get the distance. Now there's other techniques being exploited. One is to look at a galaxy here, has light in it, and the light encounters an intervening other galaxy before reaching our telescopes here on Earth, and the path lengths are different. In fact, the path lengths result in us seeing multiple images of the star. I can make it a little bigger. So for example, this one, the distant galaxy is this bright light in the middle, and these four other dots are also mirages of this galaxy. And we know this because we look at the redshift of each of these, and they all agree with the central object. We look at the spectra of all of these four, and they all have the same chemical constituents as the center one. That's 5 images of the same object. So I'm going to skip over. There's other techniques. This is another method for measuring distance using properties of what will happen to our star, the sun. It's now here on this diagram, and as it ages, it's going to follow a trajectory that goes up in this direction and maybe head over to become a white dwarf. There's technical reasons why this could be a good technique for measuring distance. So there's stuff here on lensing. There's some other topics I want to make sure I cover. So I'm going to skip some of this. Come on. Okay. Now, I am going to introduce a parameter astronomers use related to redshift, and that's called Z. So what they do is they take the observed wavelength of, for example, that example I showed earlier of calcium in a galaxy, and they divide it by the wavelength of calcium spectra measured in the laboratory. And then that ratio -1 is what they call Z. When these two are, and there's the reason why we do this. When these two are the same, for example, if we're looking at spectra of a galaxy that is standing right next to us, is not moving, the ratio of these two wavelengths would be 1. And there's a 1 here, we subtract. So that's called Z equals 0. Z equals 0 means there's no motion. Now, why is Z important? Because if you look at what Friedman and Lemaitre did, you get this very simple expression that helps clarify things. If you take the Z value of an object and add 1, that tells us the ratio of the size of the universe now to the size of the universe when the light was emitted. And we are regularly finding Z values of 7, 8, 9, 10. We even have an 11 that we've seen. And when you have a Z of 11, this side of the equation becomes 12. That means the universe was 12 times smaller than it is now when that light was emitted. And that, knowing the Z value, allows us to calculate how far away that object is now, if it still exists, and its velocity away from us. So here's an example of a hydrogen, and at different redshifts, you see these prominent peaks shift outward toward the red end of the spectrum. So I have to introduce Z because it's the way, this is the vocabulary astronomers use. So here we have, how has the Hubble constant changed over time? For very small Z, that is objects near us, the Hubble constant is the same as it is now. Where this is the ratio of today's value to some past value. So close by objects have a Hubble constant the same as we're currently measuring. As you go to higher and higher Z values, you're going back in time, and we see the Hubble constant goes up. I already depicted this earlier when I showed the same kind of graph, but I showed time instead of Z. And this is a new concept for you, I know, but it's important to understand what Z means, because look at this. If we look at the current, a nearby object, a galaxy that's close to us, that is not like Andromeda, it has a 0 Z value. With the so-called look-back distance, how many billion light years away is that galaxy? It's 0 distance. It's right next to us. As we look at galaxies with larger and larger Z values, which means their light has been traveling longer and longer, we see this curve. And before we started talking, I was pointing out this is often misconstrued in press articles about astronomical discoveries. But the Z value tells the whole story. If we find a galaxy at Z equal 4, for example, that galaxy is 23 billion light years away from our telescope. And often in the press, they will misconstrue this and assume that the farthest away anything can be is how long the light has been traveling times the speed of light. So there was just a press article the other day, light from 13 billion years ago was detected. And the author of the press article said, that means it's 13 billion light years away. Not true. It's much, much farther than that. In fact, if we go, this inset takes us to very high Z values. So the early universe is over here. And the early universe is receding from, is now about 45 billion light years away from us. So that's why you'll see in a properly composed scientific article or news article, you'll say that people think the universe is 90 billion light years in diameter, which ascribes the property of a sphere to the universe. We don't know that it's a sphere, but nonetheless, by looking at the oldest light in the universe, we know that is now about 45 billion light years away from us. So this is a critical concept to understand. The universe has been growing while ancient light has been coming to us. If it took 13 billion years for the light to get to us, the universe has been expanding the whole time. In effect, the light is swimming upstream, struggling to get to us, always going at the speed of light. But the universe is always expanding. And so that's why we get these enormous numbers for the size of the observable universe, which is about 45 billion light years. And here's the way Z relates to looking back in time. This is called the look back time. And indeed, for the highest values of Z, the most distant objects do appear to have, the light has traveled 13.8 billion years to get to us. So these are critical concepts. Now, most of you know about Einstein's idea that nothing can travel through space faster than the speed of light. And this is, okay, I'm going to keep going. If Einstein's speed limit pertained, we would never see an object receding faster than the speed of light. Depicted here is the number 1. However, the expansion of the universe does not violate Einstein's theory because the space between the galaxies is getting bigger. That only means that the universe is expanding. The motion of the galaxies in the space in which they are embedded is not anywhere near the speed of light. So what we, if doing the calculation properly, we find for ancient galaxies where Z is large, we see they are receding from us at just over 3 times the speed of light. So that's another interesting curve to keep in mind if you see press articles about how fast objects are receding from us.
Hey, Ed,
Yes, sir.
can you answer a question for Henry?
Sure, go ahead, Henry.
What happens if the space-time continuum gets stretched too much?
Okay, and so the answer is there is no such thing as too much. If there's enough energy in the universe to keep stretching space-time, it will continue to get bigger. And that's what dark energy is doing. There's no evidence that space-time is going to cease to exist. The universe is just going to keep getting bigger. Now, let's talk about, this is also critical, and I'll take a second to explain this. Here, once again, is our redshift value Z, and here's a version of the Hubble constant. And what we see is that in ancient times, that remember, Z gets bigger, that's far in the past. When Z was bigger, the expansion rate was larger. Hubble constant was bigger. And over time, the Hubble constant decreased because of the influence of matter in the universe until we get to right here, which corresponds to what I showed you a half hour ago. This is the point where dark energy has now taken control, 7.5 billion years ago. And now the Hubble constant starts rising again, and we'll see it stabilize. But if we look at these thin curves and we put them into Einstein's model, which I've done, if we had a fifth, now here's how this is how this reads. The number on the left is what fraction of the energy in the universe is matter, and what fraction is dark energy. If it was 50-50, the curve that we've calculated wouldn't be here, this green curve, it would be this blue curve. And if it was 40-60, it would be the orange one. If it was 20 and 80%, be this red one. Well, if we put in the numbers we have measured recently from a variety of different sources of 30% matter and 70% dark energy, we get the green curve, and you might expect these circles with bars are actual measurements. So what we're measuring matches, I mean, these are measurements of the positions of galaxies and their distance, or their distance and their velocity. And they have error bars, but the averages follow the theory exactly, or very closely, if we use the data taken using a variety of different techniques that give us 30% matter and 70% dark energy for our universe. So this helps confirm that we're on the right track because our measurements and our theory are matching. Now, here's a conceptual idea that I want to present, and I hope those of you who are interested, read my explanation. And if this section is called Visualization of Distant Objects, we are all used to the idea that if somebody's standing next to you, they have a certain size, and if they walk away from you, they appear to get smaller and smaller. That is not news. But in an expanding universe, that's not the case. If they're standing next to you, if a galaxy is standing next to you, it has a certain size. And if it retreats, that size gets smaller, but at some point, it starts getting bigger again. And it just is a mind-bending concept. But the fact is, and this is observed, that the most distant galaxies look bigger than nearby galaxies. And the reason is this: in an expanding universe, early in an expanding universe, if a galaxy was close to you and took up a certain amount of angle on the sky, that in the early universe, that object was close to us, so it looked big. And as the universe expanded, it got carried away, but it still was big in angular extent. And so the mathematics tells us this, and this is what we observe. In fact, another way to look at it is this: if you're at the North Pole and you send your grandson Henry out with a meter stick and he retreats from you, you're staying at the North Pole, he walks away from you, and gradually the fraction of each of these latitude lines occupied by his meter stick gets smaller and smaller until he crosses the equator. And then the meter appears to get bigger because the latitude lines are getting smaller. And in fact, when he gets to the South Pole, the meter stick wraps completely around you. And you might ask, well, how do we know we're looking at distant objects? And the answer is redshift. We can get the distance to objects from redshift using Hubble's law for distance and velocity. We measure the velocity with redshift, and that tells us the distance. So this is one of the bizarre things I referred to early in this talk about unexpected results that occur in an expanding universe. Distant objects look bigger than an intermediate object of the same physical size. Now, for those of you who have a strong heart, I'll show you very quickly some of the math that's involved here. Not going to emphasize it too much, but I do want to show you that. Whoops, I do want to show you this. So I've just been through, I talked about Hubble's work. Here's the Hubble. Now you should be seeing equations now, right? Yes, no?
Don't see equations.
No
Oh.
equations.
All right, stop. I got it. I know what happened. I got to share.
Right.
I got to share the different, I thought Windows, you should see equations now.
Yes.
Okay, so we see a simple differential equation for those of you who have had this level of calculus. Here's that A value I talked about. A dot is the expansion rate and A is the size of the universe at any given time. And it's related to the density of energy and some constants. And it's related to the curvature. That's what K indicates. But we now know from very detailed measurements that our universe is flat. And by that, I mean that all the math you learned in the 8th grade about triangles having 180 degrees and circles have a circumference of 2 pi r, that applies in our universe, even though it's a 3-dimensional object. So we can take this equation and make it simpler. We don't have to worry about curvature. There is no curvature. And we have this. This differential equation is what Friedman and Lemaitre invented in the 1920s. And if we take a more detailed look at it, Here's the amount of radiation, the amount of matter, the curvature we now know is 0, and the dark energy. And the radiation dilutes as 1 over the size of the universe to the 4th power. The matter dilutes as 1 over the cube. And then we have a differential equation we can solve. And that's where those curves come from I showed you earlier. And when you solve the equations, you get hyperbolic sine functions. And if you want to look at the expansion rate, you get hyperbolic cosines and hyperbolic sines. And from this, we can calculate numerically what is Hubble's constant as a function of time. And it's a hyperbolic cotangent. And it has the different parameters in here. This is the equation I used to draw the graphs I showed you earlier. So if you put this all together, you get, these are the graphs. And some of them are shown in a little different form, logarithmic form. But here are depictions of the history of the Hubble constant based on this equation right here. Now, the same thing applies when we look at this very complicated curve I showed. That's how I did these curves, these thin curves using different values for the energy density in terms of matter and dark energy. The only one that works is the one that we have observed, 30% matter, 70% dark energy. Here's the Z value that I talked about, which is related to how big the universe is. If you know the Z value, that tells you how the universe has expanded. There's the Doppler shift. Here's the curve I already showed you. This is looking back in time, how big was the Hubble constant? It was bigger long ago, but it's settling into a constant value that we understand. And we can look back in time using the inverse hyperbolic sines. And that gives us the look back time curve I showed you. You saw this curve. Here's the Einstein equation. This is the equation that limits your velocity through the space you're in, and its maximum is the speed of light. But this is the velocity relative to us, and it depends on the Hubble constant looking back. And that's what gives us this curve that says most distant objects are receding from us at up to 3 times, a little bit more than 3 times the speed of light. Here's some arithmetic here. And I'm going to stop at this point because we're out of time. But there's detail in this chapter about how Friedman and Lemaitre did their calculations and how we get to these expansion curves of t to the 2/3, the square root of t, and the exponent of t. So with that, I'm going to stop. And if there are questions, I'd be happy to entertain them.
I have a question. Yes, that was nice. Thank you.
Okay,
Ed,
good.
so you throw around this number for dark matter and dark energy, which we really know nothing about. And we've been trying to detect both of these things. If I remember right, we're still trying to detect any of this stuff, and we haven't.
Right.
It's just there.
Yep.
So is this just a big fudge factor for now until we figure out what it is?
Well, it would be, except for the following thing. We have 4 or 5 different independent methods for measuring dark energy, and they all agree on the same value. And I'm going to show you one of them. One of them is something you may have heard of called the cosmic microwave background.
Yes.
It very precisely pins down the amount of dark energy in the universe. There's not any wiggle room at all. A different strategy is to look at these lensing events for dark matter.
Yeah. All right.
And in addition, the cosmic microwave background very clearly says that our universe is flat, geometrically flat. Now, I'm going to stop sharing because I want to show you what I mean by that. You should be able to see me. This is a flat piece of paper. If I draw triangles and circles on it, they all conform to what we all learned in the 8th grade. this has not only a flat shape, it has a flat geometry. But if I take that same shape and I roll it into a cylinder like this, it's the same piece of paper, and it has triangles and circles drawn on it, and it is flat. It has a flat geometry, but not a flat shape. Clearly, it's not a flat shape. It's now a cylinder.
Okay, all right.
But geometrically, if you investigate, if you go in there and take a protractor and measure how many degrees are in triangles, or how big the circumference of a circle is relative to its diameter, you'll get the same answers we got in the 8th grade. So this is a perplexing thing, that our universe is three-dimensional, but we know it has no curvature. So that having no curvature tells us the total amount of energy in the universe. That confines it very specifically. But the cosmic microwave background is not the only way this is done. It's also using supernova events, lensing by galaxies.
Right.
And so we have 4 or 5 different independent techniques. I agree with you. We do not know the source of dark energy or dark matter, but it's not something that one astronomer picked to make his observations agree with theory. They all get the same numbers, 30% and 70%.
Wow. So do we know enough to figure out that we can figure out what it is, or are we still in the dark about that?
We're, in the dark. Well, here's what's happening. Worldwide, people are scrambling. People at CERN, the big accelerator in Switzerland, are looking for a whole new class of subatomic particles that might be the source of dark matter. And there was a theory called supersymmetry that was a candidate. They looked for it in the prior version of CERN's accelerator, could not find it. So they shut down for 3 years. They upped the energy. They just restarted last week. They're at the highest power level that's ever been seen on Earth. And so they're scrambling to see if they can find supersymmetric particles. There's theory out there for a variety of things. For example, could primordial dark holes be dark matter? That is, in the events that occurred around the Big Bang, did a whole bunch of tiny black holes, too small to be detected, did they create the dark matter that is the reason that the galaxies appear the way they are? I made a passing comment earlier that dark matter dictated the formation of galaxies. And I did not show you the details from another chapter in the book tonight, but we know why the galaxies formed where they did. That's strongly linked to the temperature variation seen in the cosmic microwave background. We can actually see the connection between temperatures and where galaxies formed. And the question is, were there primordial small black holes that seeded the formation of galaxies, or did galaxies form and black holes formed within them? We don't find evidence yet for mergers or other evidence of tiny black holes. We have, of course, seen mergers of mid-sized black holes using the gravitational wave sensors here in the US and in Italy. But a possibility is that dark matter is explained by tiny black holes, the size of the sun or slightly smaller. They can't be too small or they evaporate. So they have to have some serious mass. You would not want to approach one of them. That's a possibility. There's probably 8 or 10 explanations being considered for dark matter. Dark energy, if you're willing to stick with me for a minute, I'll tell you that a theory emerged in the late 40s dealing with how much energy is in a vacuum. I may have lectured on this. Bruce maybe remembers if I lectured on the Casimir effect. Mm-hmm. And in the late 40s, Casimir, a Dutch scientist, using new techniques in a field called quantum electrodynamics, said an empty box should be churning with virtual particles, and those virtual particles would have energy. And he was scoffed at, and people thought he was crazy. But 50 years later, an experiment was done to prove that that energy, in fact, exists in a vacuum in a laboratory. And astronomers said, hooray, finally we have an explanation, until they compared the numbers. The astronomers measure the amount of energy needed to make the universe expand the way it does. And the physicists in the lab looked at the Casimir effect, and they measured the energy in an empty box. And when you compare those two numbers, the expectation was they would be the same, but they're not. They're different by 10 to the 120th. Nobody knows why the energy density in the cosmos is so dramatically small compared to what it is when you measure the energy in a vacuum in the laboratory. It's a good thing it turned out that way, because if the laboratory value prevailed, the universe would have expanded so rapidly in its early days that hydrogen gas would have never formed stars, and galaxies would never have formed, and we would not be here to observe the universe. So why is there this stupendous difference between the energy in empty space out in the cosmos and the energy in empty space in a laboratory? No one knows.
Mysteries abound. Wow.
Now, yes, go ahead.
Thank you, Ed. It was a fascinating talk, as always. I'm surprised by the paucity of black lines in the spectra that you show, and it looks like they're all in the example you showed of calcium.
Well, that's just to make it simple. An actual
Oh, I see. I thought that was the actual. And I said, well, how do you know you're just picking calcium? Because there would be hundreds of lines.
No, the spectrum of a galaxy is incredibly complex, and that's why we have graduate students, because they have to pick through all this and write code to tease out the different atomic material, the elements and their isotopes. But the one I showed is just to make it simple enough that a non-scientist can grasp what's going on. But no, a spectrum of a galaxy is extremely complex.
And so when they do the redshift, they have to go to the same line in the two places. And there are so many lines. How common is it to misidentify?
All right, so now, at some point, Bruce is going to get exhausted and tell us that we have to stop. But until he does, I'm going to keep going. So this is what I showed earlier. So this is oxygen and 2 hydrogen lines. And if you take the spectrum of gas, like a cloud of hydrogen gas, you can find these isolated lines. If you look at a galaxy, it's just overwhelming with the amount of information that's there.
Yeah, because they have all the elements. I mean,
yes.
Of course, it'll be complicated also by the abundance of the element.
Yes. And the intervening gas and dust between us and that galaxy will influence how the lines come through. So astronomy is both grand in its ambitions and very detailed in its activities, where you have to just dig through mountains of data and make sure you handle the dust correctly and all that sort of stuff. So what I'd like to do, I can keep going. It's up to Bruce when we stop. But people, you should, if you don't have my email address, you probably have it, because of all the communications gone back and forth, and I'd be thrilled to hear from you. So we get more questions, so I can think more deeply about how, not only how much I understand, but how to present it in a digestible way. And I have to say, I just got through giving this very similar lecture to the group in England. One of you gave me a recommendation to speak to a group of engineers in England, and I've done so twice this year, and the IET. And so I get great feedback from them because they ask very penetrating questions, and I'd like that from you as well. So I can keep going. It's up to Bruce.
We have 4 more minutes.
Okay. Let's see. There actually are a couple of questions. What happens when space gets stretched too much? We don't know that there's any limit to that. In fact, black holes prove that stretching of space or space-time has no limits, because black holes exist, and the curvature that goes on deep in the black hole near the singularity at the center is enormous. And yet black holes exist. They don't blow apart. They become, when they form, they become eminently stable and will last for the rest of the life of the universe. Is there any way to tap into a small amount of dark energy to solve the energy crisis? Everybody wishes. Here's the problem. As I pointed out, the dark energy density that we see out in the universe is so tiny that it takes volumes on the scale of tens of billions of light years to make it have any influence. So sadly, the energy density seems to be way too small to have any practical use. Peter asked, what are the leading astronomical instruments gathering data? Well, the cosmic microwave background has been an enormous benefit in fueling our knowledge and probing the structure of the universe. It was just a revelation to have it come out the way it did 30 years ago, and then successive experiments. I think some of them I've talked about in this forum. And so the cosmic microwave background, enormous effect. Supernova events of type 1A, so that we have standard candles that let us reach way out into the universe and measure velocity versus distance. And I picked the right, hang on. I'm going to remind you of what I showed earlier. That's also been an enormous breakthrough in technology right there. Supernova data. So, and there's others, gravitational lensing, computational techniques. The whole time though, Einstein's theory of gravity has been standing as a reference beacon for how to digest this data and see what it means. And it's been tested over and over again. No flaws have been found so far. It may be incomplete, but it's the foundation upon which all of our theory depends. All these curves I showed you, like this and these, they all come from Einstein's theory of gravity. And as I pointed out, where is it? They match the data. So anyway, I can't find the right curve right now, but so we have a lot of tools, and James Webb is going to be a big help as well. Oh yeah, here's the one I wanted to show you. This curve with all those hyperbolic functions in it comes right out of Einstein's work.
Okay, so I think we're going to stop the recording now.
Okay.
And